Anywhere from 70 to 90% of the power consumed by a municipal plant goes towards pumping, either pumping water into the plant and out of the plant, or pumping wastewater into the plant and out of the plant. What you need in that plant is basically to have a pump system that can handle the high flow rates at the peak flow and the low flow rates at the off-peak flow.
Hello and welcome to the Pumps and Systems podcast. I'm your host, Tom Baer, a managing editor at Pumps and Systems magazine. Today we're speaking with Kevin Haggerty, Garry Queen, and Dillon from Dynamatic, and they're going to be telling us all about the differences between variable frequency drives, or VFDs, and eddy current drives, or ECDs. So without any further ado, let's get into the episode. Kevin, Garry, and Adam, welcome to the Pumps and Systems podcast. So how are you all doing today?
Fantastic.
I'm doing great, thank you.
Really well, thank you.
Great. Okay. So today we are going to be talking about eddy current drives versus variable frequency drives. But before we get into that, would you mind just introducing yourselves? So tell us a little bit about who you are, what you do, anything that you think our listeners and viewers might want to know.
Okay, well, I'll go first. My name's Kevin Haggerty. I am the business development manager for our municipal water and wastewater plant. I handle all the sales in North America along with Garry. We basically have the whole US and Canada as our territory. We've basically divided up that territory, so we each cover half of it. And like I said, we take care of all the sales in the municipal world.
All right, I'll hop in. Dillon, industrial market manager. So I handle everything on the industrial side of the business. So all of our verticals, so metal stamping, extrusion, wire and cable, crane and hoist, all of those verticals are in my purview.
I'm Garry Queen. I'm sales application engineer for the municipal water market. And as Kevin said, we split the country up and Canada included in half. And we both have the same amount of reps and stuff. We help support business and work with customers with respect to technical issues and sales and all that good stuff. So it works pretty good.
All right, great to know a little bit more about you. So then let's move into our main topic for this episode. So first, could you tell us just the absolute basics? Like, what is an ECD and what is a VFD? Because I personally have heard of a VFD, but I don't know very much about ECD, so I would love to know more about the difference.
I guess I could start there. So the difference between an ECD and a VFD is, for one, the eddy current drive, or the ECD, is a electromechanical device. It's actually a part of the pumping mechanism itself. So when you install an eddy current drive, if you had a constant speed drive pump system, you would have a pump and you'd have a motor mounted to the head of that pump. If you want to install an eddy current drive, you're going to remove that motor from the head of the pump. You're going to install the eddy current drive to the head of the pump, and you're going to install the motor to the head of the eddy current drive. So basically that eddy current drive becomes part of the rotating equipment itself, versus a VFD, which is more of a electronic component. It doesn't spin or rotate with the motor and the pump itself. So it's not, in the assembly itself. It's basically an electrical unit that sits on the side of the plant, adjacent to the pump and the motor and the unit, or it's located in an adjacent control room. So it's not part of the rotating assembly, and that's probably the biggest difference. The other difference is the eddy current drives have been around since the 1940s, and VFDs have been on the market since, say, the 1980s. So we like to say the eddy current drive is a much more proven piece of equipment, and it's been used in the industry for a lot longer time, and it has a lot of benefits to it that we'll get into as we go through the podcast.
All right, great. Thank you for that primer. That definitely helped me out. So then let's talk about variable speed drives, first of all. So why are they beneficial in most pumping applications?
Well, I guess I'll just continue talking since I have the mic.
Go for it.
The reason why the variable speed drives are beneficial in a pumping application in a plant, and now we're talking mostly municipal, could be a drinking water, it could be a wastewater plant. It's highly reported that the pumping part of the plant is the overall power consumption that's used in a municipal plant. It's anywhere from 70 to 90% of the power consumed by a municipal plant goes towards pumping, either pumping water into the plant and out of the plant, or pumping wastewater into the plant and out of the plant. And regardless of if it's a drinking water plant or a wastewater plant, you basically have what's called a peak flow every day, where you have very, very high flow rates. And then you have your off-peak flow during the day, which is at the lowest flow rates. What you need in that pump or in that plant is basically to have a pump system that can handle the high flow rates at the peak flow and the low flow rates at the off-peak flow. If you don't have a variable speed system incorporated with your pumps, you basically only have two options to control the flow. Either your pumps are running all the time when you need the full flow rate, and then you turn them off and you wait for that, your dry pit or your wet pit to fill back up and restart your pumps. Or you can have a set of valves that when you're running your pumps all day long at full speed, you're opening and controlling valves to control where that water's going. Neither scenario is great, because when you're running the pumps full speed, you're consuming a lot of power. When you're starting and stopping them multiple times a day, you're creating a lot of wear and tear on the component. So when you incorporate a variable speed control on a pump in a municipal plant, what that allows you to do is speed up the pump and increase the flow rate, decrease the speed of the pump and decrease the flow rate. And you're not having this hard start and stop all day long. And you don't have either a plant control system or operators running around and opening and closing control valves all day long. So, when it comes to mechanical stuff, I always like to incorporate sort of the car comparison. You think about a car being driven in the city, starting and stopping all day long. Well, that car is going to use much more gas and have a much higher maintenance bill than a car that's being driven on the highway and just gradually speeding up and gradually slowing down. And having that highway driving is sort of like having a variable speed system incorporated with your pumps. And that's kind of how I like to look at it. Garry, do you have some things you want to add?
The biggest thing that I see in municipal pumping applications for using variable speed, not only do we save in terms of wear and tear on equipment, like Kevin mentioned and all that, but there's also considerable energy savings. Anytime you slow an electrical motor down, you save power. It's just that simple, okay? In the case of where we're dealing with municipal pumping for fresh water, for wastewater, the majority of the pumps that are used are centrifugal pumps. And these are considered variable torque loads, and they happen to fall under the pump and fan affinity laws. And the pump and fan affinity laws tell you that capacity of a pump is proportional to the speed of the motor. So if you're pumping at 100%, you're getting 100% capacity. It should be fairly intuitive. When you slow it down, say 10%, your capacity goes from 100% to 90%. But now some things change. The amount of current that it takes to drive the pump actually drops a little bit more because the amount of torque varies with the square of the speed. So if we drop from 1.0 or 100% to 0.9, the torque drops 0.9 times 0.9, or drops 19% to 81%. But most importantly is the power, because the power varies with the cube of the speed. So if we change the speed by 10% to 90%, the actual power consumption drops to 72.9%, which is effectively 0.9 cubed. The beauty of this is there's tremendous savings. As Kevin alluded to, most pumping systems vary between 70% and 100% of capacity. Much below 70% and flow drops off, and it's not economical to run in those areas. But in that bandwidth of 70 to 100%, you save a ton of money. And at 70% speed, as an example, you're drawing 65% less power than you would be at 100%, but you're still pumping at 70% capacity. So the pump and fan affinity laws do come into play. I will say parenthetically that I've given you ideal numbers that you would say 27% for a change of 10% capacity, but most pumping systems are not free of losses, such as static and dynamic head or pressure that you have to pump against. So there are some losses, and while saving the cube of the speed is a theoretical good value, you won't quite get there. And with that said, I think Adam's got some things to add here.
On the industrial side, we see, pumping applications in steel mills and paper mills. So the product that we use are liquid cooled couplings. So, they're operated anywhere from around 200 horsepower up to 3,000 horsepower, depending on the size and flow and whatnot. So, primarily that's where we see the product. I mean, that's about all I have to add for that.
So then if you're choosing a variable speed drive, what are some important things that you should consider?
Looking at pumping systems, you got several things going on. You have the driven equipment, which is the pump. And we kind of talked about centrifugal pumps for a good part here, but also in plants, whether they're industrial or municipal, you're going to see pumps of all kinds. Centrifugal is just one. You've got positive displacement pumps, you have rotary load pumps, you have progressive cavity pumps. So we have to look at the driven load. In the case of centrifugal pumps, they fall under the category of being a variable torque load, meaning that the load changes as the speed of the pump changes. With respect to positive displacement, progressive cavity and rotary load pumps, they demand the same amount of energy across the speed range. The power does go up and down, but the amount of torque that it takes to drive not only the motor, but also the pump itself is constant across the speed range. So you have to take that into account when you're sizing up a variable speed system. The other part that you need to consider is not the driven load, but also what you're going to interface to with respect to the control system or the automation system. And you need to get a good lay of the land on that, because there are multiple applications. We talked a little bit earlier about influent, effluent, but there's also aeration. But then in other applications within any given plant, you may have sludge you have to pump, or viscous material. There may be metering that you have to do with respect to adding, say, polymers to a water and stuff like that. So you have to consider also the controls that you're integrating to. So that affects the overall variable speed drive that you're going to use. In the case of a centrifugal pump, you'd use say a VFD. You would use a VFD rated for normal duty. And what normal duty means is that the drive or the load actually won't require real high currents in terms of trying to overcome some kind of physical anomaly like the viscosity of the liquid being pumped, or other things that could come up with respect to pumps and motors that require a little bit more current. Normal duty applications are typically 10 to 20% extra capacity in the variable speed system for variable frequency drives, and for heavy duty loads such as positive displacement pumps, progressive cavity, and so on, they actually have 50% capability above their 100% rating, where they can operate for a minute at 150%. The reason why manufacturers of VFDs do that is because they can take a standard VFD that's rated, say, 10 horsepower normal duty, and then for a heavy duty load, it's re-rated to 7.5. So you actually save money whenever you can use a normal duty rated VFD on a pumping application versus a heavy duty VFD. Similarly, with eddy current drives, we basically apply those by taking a look at the pump curve. We're predicate everything based on brake horsepower on the pump curve. And it's pretty much that simple. We don't really delve into normal duty and heavy duty quite as much, because the magnetic coupling inside the eddy current drive will transmit whatever the motor is telling it in terms of torque that it's producing. So the eddy current drive will transmit up to breakdown torque of the motor, which VFDs typically are not sized for. That actually requires oversizing the VFD considerably to reach those kinds of torques. So there's an inherent advantage with the eddy current drive with respect to torque. We do have some notes in here about matching electrical characteristics and stuff. That is very important, especially with respect to VFDs. The number one thing applying VFDs is that you look at the motor nameplate and you look at the full load amperage on the motor, and you make sure that your VFD can supply that or a little bit above that so that it can perform appropriately. And with that said, Adam, I think you've got some things you'd like to add.
Yeah, to piggyback on what Garry was talking about in terms of having to oversize motor and VFD for stamping press applications on the industrial side, typically we recommend, if a customer is replacing an eddy current clutch and motor assembly, we recommend upgrading 2 motor sizes. So for instance, if you have a 50 horsepower eddy current clutch and motor assembly, you would probably have to have a 75 horsepower VFD and motor, and that's to have the same starting torque, which is important in that particular application. So that's something that customers will have to factor in terms of cost and whatnot, when they're comparing the two technologies.
So we talked about the basics of these two types of drives, but let's talk a little more in depth. So can you tell us a little more about how each drive technology works?
Absolutely. I'm going to start by talking about VFDs. When somebody said to me once, I thought it was pretty funny. I was explaining how a VFD works, and the basics of it is the VFD takes AC power from your wall socket, your 3-phase power in a plant, and it takes AC, makes DC, and then chops it up, and the motor takes it as chopped up DC. And somebody said to me, that sounds like electrical gymnastics. I thought that was pretty funny, because in a way, it sort of is, because you're taking AC and you're converting it to DC, and then you're playing a little game with some switches. The garden variety VFD does do that exactly, and it's basic control mode in order to, and it starts with the constant torque load, and then it's shifted over to the variable torque because it's easier to do. In constant torque loads, what has to happen for the VFD to provide torque across the speed range that's the same is that the voltage and the frequency, it's a ratio, voltage divided by frequency. That ratio needs to remain constant from basically very low speeds to base speed of the motor or full speed. And that allows you to do constant torque. And similarly, when you apply that to a pump load, a variable torque load, because the VFD can supply that constant torque across the speed range, it's no problem to do the centrifugal pump whose torque varies with the square of the speed, as I mentioned earlier. As a part of controlling those VFDs, you got several things that come up. With respect to the input side of it, we're switching AC and making DC. And when that happens, there are certain nonlinearities that occur because of the switching mechanism. And you have to take a look at what that VFD is producing on the input side of it. There's some issues that need to be addressed, most notably harmonics. It's not all that critical in most applications, but sometimes it can be. Then with respect to the output side of the VFD, we have to consider the length of the cables going from the VFD to the motor, because there can be some issues there. Now, with respect to torque, going back to that, we talked about constant torque and variable torque. And then sometimes you get into a situation where you need considerably more torque in industrial applications. And I've seen it personally in working with positive displacement pumps. When you're pumping very viscous materials, you may exceed that 150% rating I mentioned a little bit earlier. And when that happens, you do have to oversize the VFD considerably, as Adam mentioned as well, even though it is a pumping application. The unfortunate part is that most of the modern day VFDs fall under a sensorless vector and closed loop vectors. Then they simulate a volts per hertz control for the very basic control. So what happens is, in those cases, those VFDs are limited to roughly 172% torque when an application may require that you produce 225 or 250%, which would actually play into the hands of using an eddy current drive. Most of the drives are pretty much, the VFDs are pretty much the same from manufacturer to manufacturer. They pretty much all have the same benefits and features and similarly the same side effects, if you will. And that's pretty much about all I can say about VFDs. They keep voltage and frequency constant in a ratio, which produces constant torque across the speed range and simply takes care of those constant torque loads. And it makes it easier for doing variable torque applications like centrifugal pumps and fans. I believe Kevin's going to handle eddy current drive.
Thanks for that, Gary. I think an explanation of the eddy current drive is what you'd like to have. And first of all, what I'd like to say is we call these devices eddy current drives, but in the past, people have referred to them as eddy current clutches. They've been called magnetic drives. They've been called magnetic clutches. So there's various names that have been used throughout the generations of these things, but regardless of what you call them, they basically all operate the same way, and that is that they provide a method to control the speed of whatever they're connected to. In our case, usually in a municipal plant, it's a pump, but it could be other devices like a mixer or a blower or a fan. Wherever you want to control the speed of a device, the eddy current drive can be used. Now, basically, the eddy current drive itself, like I said before, it physically sits between the pump, in the case of using it on a pump, between the pump and the motor. As far as internal components go, the drive itself has a drum that's located inside the eddy current drive that's connected to the shaft of the motor. And it also has a salient pole rotor that's connected to the shaft of the pump. Other internal components in the drive, we basically have a clutch coil, we have a tachometer, and then you have some bearings that support the weight of the drum and the rotor. It's important to note that this rotor basically sits inside the inner diameter of the drum, but they're not mechanically coupled or connected to each other. There's an air gap that separates the drum from the rotor, which is a pretty important aspect of the drive itself, because that's really what leads to the longevity of the drive. There's physically no rubbing, touching, connected components inside this drive that cause it to wear out in any period of time. And that's why you'll see eddy current drives in the market that last 50, 60 years before they need to be replaced or refurbished. But basically, the way you operate an eddy current drive, when we start up the system, it typically is equipped with an AC motor. That AC motor runs constant speed, full speed, the entire time you're operating the drive. And the reason that's important to note is because since you're driving it like the car on the highway, you're not stopping it, starting it, slowing it down, speeding it up. That AC motor runs at full speed the entire time you're running the eddy current drive. The way we control the eddy current drive, like I said, the rotor shaft is connected to the pump. It has a control coil inside of it. By varying the voltage that we put into that coil, we cause a magnetic field to be generated between that drum, the inner shell of that drum, and the rotor that sits inside of it. The more voltage we put across the coil, the more that rotor spins and chases the speed of the drum. So since you have the motor running full speed, the drum's running full speed, we can speed up and slow down the rotation of that rotor by putting higher or lower voltages across the clutch coil. So that's basically how you control it. The tachometer that's inside the unit provides feedback of the output speed to the controller. The controller is the unit that's varying the voltage across the clutch coil. And so you basically have a closed loop system where we're monitoring the speed of the unit. And if it needs to be increased or decreased, we control that by increasing or decreasing the voltage across the coil. It's this sort of straightforward design that's in the unit that basically, like I said, gives the eddy current drive a lot longer life expectancy over a VFD. The only items that need to be maintained in an eddy current drive are the bearings need to be lubricated, periodically. Normally, this is part of the routine maintenance. When the maintenance guys go in to lubricate the bearings on the motor, they can lubricate the bearings on the eddy current drive. And then there's also a set of brushes inside the eddy current drive that need to be checked and replaced periodically. The number of times they need to be replaced in a given year, of course, depends on how many operating hours are put on the ECD. But in terms of maintenance, the plant personnel can maintain the VFD relatively easy. And like I said, because it's mounted as part of the rotating equipment itself, there's no large, VFDs sitting on the side of the room. That's a pretty basic explanation of an eddy current drive.
So then it sounds like the lifespan and kind of the ease of maintenance are some of the benefits of that kind of drive.
Oh yeah, I mean that's actually one of the big benefits. We find that a lot of times a city will hire a consulting engineer, and the consulting engineer will come in and do a study and look at the lifetime or look at the technologies, VFD versus ECDs. And probably two of the largest, most common attributes that they say that the reason you would want to buy the ECD over a VFD is the ECD is going to last considerably longer in any application. And the plant personnel can perform all the maintenance required on an ECD, where that can't always be said for a VFD.
Kevin, I'd like to piggyback on what you said. Another key factor is actually ease of installation. So typically VFDs require special climate control environments, whereas eddy current drives are air-cooled. They're self-contained, air-cooled, so they don't require any special accommodations. And actually, we have a number of large extrusion customers in Texas that have had our liquid-cooled couplings outdoors operating for decades with no problem. If a customer was going to replace our technology with a VFD, they'd actually have to construct a separate building to house a VFD and have it climate controlled and whatnot. So there's a cost associated with that. So our value proposition is total cost of ownership.
All right. So then along those same lines, let's talk some more about some of the benefits of ECD versus VFD. So we touched on the lifespan and the maintenance, but what are some other benefits?
One really large benefit that you have when you install an eddy current drive, and Garry touched on this earlier, an eddy current drive doesn't create any harmonic distortion across the line. So when you don't have harmonic distortion, you don't have to have any harmonic mitigation equipment installed, or what's called a harmonic filter, which is very important. We've seen recent bids in the marketplace over the course of the last year for some harmonic filters for some municipal plants, and the dollar range of those bids can reach several $100,000. And I'm not talking $100,000 or $200,000. I'm talking a harmonic filter system for for an average size municipal plant could be $300,000, $400,000, $500,000. If you have an eddy current drive system that doesn't create those harmonic distortions that you then have to treat for, you can eliminate the requirement to be spending those extra dollars to handle that. Another benefit of the eddy current drive is that it's not affected by the power quality. If your plant happens to be at the end of the power grid, or if you need to run that plant from time to time off generators, this will not affect the performance of the eddy current drive, but it'll certainly have an effect on a VFD in the same application. So another rotating equipment benefit of the eddy current drive is the eddy current drive, you don't have what's called fluting occurring in the system. Fluting is a condition where current builds up on the shafts of the motor. It gets discharged through the bearings of the system. That discharge can cause pitting on the bearings, and that pitting can cause premature lifetime failure of the bearings as well. So that all gets eliminated with the eddy current drive. And then lastly, all that is sort of piggybacking what Adam said, because an eddy current drive uses a very simple, small digital control system that's housed in a very, let's say, a smaller control panel. That control panel typically takes up about 60 or 70% less space required than what you have for a VFD. The fact that you don't have the additional space, the fact that the control system is relatively simple in design. It doesn't create a lot of heat. You also then don't need either a self-contained cooling system, an air conditioner or a water-cooled system like a VFD will require. You don't need any of that with an eddy current drive. So I think there's some of the big benefits. I think, Garry, you might have a couple you want to add as well.
Kevin touched on generators. That's a big deal. A lot of these plants do have backup generators. I know that in some states like North Carolina, they've mandated every pumping station, whether it's wastewater or freshwater, have a generator. Whenever you have a load, as Kevin alluded to earlier on in our conversation, that pumps take up 70 to 90% of the total load in these plants. You can imagine the size of the generators that you have to have. But when you're running VFDs, because they are nonlinear, instead of just a motor across the line, you've got basically an electronic switch in front of the motor. You do have to oversize the generator to compensate for that nonlinearity. So it does add costs. You don't need to do that with an eddy current drive, because basically we're taking our input from a motor and we're coupling it to the output shaft of my drive. And it takes a lot less power to do that. One of the key benefits of the eddy current drive is that, as Kevin said earlier, the drive is between the pump and the motor. And basically, by not giving a signal to the eddy current drive, you can literally isolate the motor from the pump. In order to do that with a VFD system, you have to put a contactor between the VFD and the motor. And if it's under load, you can actually cause that contactor to open under load, which is not a good thing, because it can cause problems with the output switches of the VFD. And over time, they do degrade. And most folks, what we see in the field is contractors won't get a contactor with an auxiliary, which you can tie it back to the control system on the VFD to shut the VFD down prior to opening that contactor. So that's a small little thing. They call that slamming for the VFD world. And with respect to the other end of the motor, we had talked about motor leads being of issue. Kevin touched on one problem with respect to shaft grounding currents. So basically, this high frequency output from the VFD, it causes a couple things to happen. It causes parasitic capacitance to build up on the motor cables. And the longer those motor cables are, the greater the parasitic capacitance. So you have to take precaution in that. And some of it could be adding load reactors to the output of the VFD, or adding DVDT filters to the output of the VFD, or adding sine filters to the output of the VFD to clean up that parasitic capacitance, because it can be, I should say, catastrophic to both the motor and the drive itself. Also, some of the benefits of VFDs are that they can run submersible pumps. We can't put an ECD on a submersible pump because we can't get between the motor and the pump. So by default, we can't do that application. Now, VFDs do have multiple microprocessors on board that do multiple different things. Some of it is not only doing the motor control, but also there might be heavy networking concerns from some of the owners of it, to where they need to communicate a lot of data from the VFDs up to their SCADA systems and stuff like that. So they do have multiple processors for that. And their networking is pretty nice. VFDs can also be powered from DC systems directly, such as batteries. Today, with all the pressure on people to use renewables, such as solar power and wind power and all of that, that's all pretty much DC before it's inverted to be put onto the power line. So you could actually run a VFD directly from those outputs, provided it's the right value. And VFDs do have one last nice feature that needs to be brought up, is they can be controlled. The current output can be turned down such that they can start a motor without inrush current. It's typically not done. It could be on pumps, which is an ideal application, especially centrifugal pumps, but not so much positive displacement, progressive cavity, or rotary load pumps. So you can control your inrush current with respect to the VFD if you know how to apply them properly. With that said, all in all, the VFDs are a nice product to use. They typically have a lifespan. They're designed for 100,000 hours based on the core of the VFD, which is their capacitor bank. They're rated for, as I said, 100,000 hours, which is 11.3 years. So they should get 10 to 12 year life. If they take really good care of them, you could probably get 20. The driving concern there with VFDs is because their manufacturing runs are typically 3 to 8 years long. That means that every 3 to 8 years, a new version is coming out, which means that spare parts could become an issue. With respect to eddy current drives, on the other hand, we've been making these things since the mid-30s, 1930s. So they're pretty much the same. We rebuild our customers' products back to factory standards, even after 60 years of operation. So there's a tremendous benefit with respect to that.
Yeah, I mean, we worked on a rebuild of one of our liquid cooled couplings that was being used to test helicopter blades by a government facility, and that unit was originally built in 1966, I believe, and we restored that to original OEM standards. We also have a large extrusion customer in Texas who frequently sends units back to us for repair, and most of those were built in the early 60s.
How long in general does an ECD last? It sounds like quite a long time.
It depends on the application, but it's not uncommon for a eddy current unit to last 30 plus years. The other thing that we didn't mention is motor wear. So the way our design works is the motor that's connected to the eddy current, whether coupling or clutch, runs at a constant speed. And VFDs obviously vary the speed of the motor. That tends to burn out the windings relatively quickly. So in a couple of years, maybe 3 to 5 years, you're looking at a new motor. Now, if you're looking at an extrusion application that's a 2,000 plus horsepower motor, that's a lot of money. To consider in terms of total cost of ownership. Whereas with eddy current units, it's not uncommon for us to get a clutch and motor assembly that's been on a stamping press for 50 years, and we get it in, we repair the clutch, and we don't do anything with the motor because it's still in great condition. They run at one constant speed, and there's no wear on it.
Okay, so before we wrap things up, is there anything else you want to add or any closing thoughts you have for our listeners and viewers?
I guess the one thing I'd share is I've been with the company now a little over 2 years, and the number of plants I visited that have had both technologies, the eddy current drive, and then there's plants that have the VFDs. And a lot of things we talked about here today, the benefits of the eddy current drive versus the benefits of the VFDs. I haven't walked into a plant yet where they've had an eddy current drive that's been there 30, 40 years, and they weren't, I hate to use the word totally satisfied, but very satisfied with the performance and the lifetime that they got from that unit over the years. And I can't say that so much for the VFDs, and not to put the technology down. The technology is great. It has its place, but it's limited lifetime and the complexity of it that makes it difficult for the plant people to operate on. They're the things we hear a lot. And when you walk into these plants, it's not uncommon for them to have 10 or 12 or 15 job openings. They're lightly staffed. They don't have the manpower, and they especially don't have a high level of people that can go in there and work on complicated equipment. And I think that's the difference between what we really see. The eddy current drive, it's old school, it's nuts and bolts, it's very easy to work on. And the VFD is a more modern electronic system that it just has a level of sophistication that's not that easy for plant personnel to work on.
I think that's great, and Kevin's 100% spot on. And when you start looking at applications where you're using medium voltage motors, which is really important for customers because many of our customers are required to keep a level demand curve with respect to the power that they consume. And because of that, they have to keep their inrush currents as low as possible. And the biggest way to do that is go with the medium voltage motor, which draws less current. The unfortunate part is if you use a VFD in the case of a medium voltage motor, it requires a highly skilled individual to perform maintenance on the VFD. And they're not just around the street corner. These are factory trained people with degrees in electrical engineering and so forth doing maintenance. So they're pretty much a scarce commodity, if you will. But with any current clutch, as long as the technician has a screwdriver and a grease gun, he can pretty much do maintenance. Many of our smaller eddy current drives up to 449 T-frame, typically all you need to do is just re-grease the bearings, the pilot bearing and the load bearing on the eddy current drive. In the larger ones, when we move to salient full, as Kevin mentioned earlier, those do require a little bit of work on brushes, but it's pretty simple. Our procedure makes it a 5-minute operation to replace and set brushes up for eddy current drives. And then the last thing I would mention is when we work with our clients to determine if they want to use a VFD or an eddy current clutch, we talk about life cycle costs. As we mentioned, Adam has mentioned some very difficult applications such as punch presses and extruders. Those are brutal applications. They really are. They're hard on the motor, they're hard on the drive, and the eddy currents live 30 and 40 years. There's not a VFD manufacturer that can claim that. That's a fact. So in the municipal world, they tend to last longer because they're not in such a brutal application. I've worked on one in a power plant. The eddy current drive was put in operation in 1956. We will be replacing that in October of this year. So you can do the math. You can see it's quite old. So we talk about life cycle costs, and we factor in, the life of the product, the efficiency of the product, and then we compare it with the competition, which is typically a VFD. And generally, you'll find that in terms of a 60-year lifespan, the ECD is the optimal way to go. And given our pursuit, our market pursuit, that is, of the municipal market, that market's going to be around forever. So as long as there's civilization, we're going to have the need to process wastewater, and we're going to have the need to pump fresh water. And that's all I have. Thanks for having me.
Okay, well then I will say thank you so much for taking the time to talk with us today. We really appreciate you sharing your expertise with us.
Thank you.
Thanks.
Huge thanks to Kevin, Garry, and Adam for taking the time to speak with us today about ECDs and VFDs. If you've enjoyed listening to the podcast and would like to watch it, hop on over to our YouTube page for the full video version. That's going to do it for today. Thank you so much for listening or watching, and we will see you next time.